Hi students, welcome to question bank 25. Today I'm going to discuss the wave equation, and this is a partial differential equation which is extremely important, and in many interview setting if people are going to ask you questions on PDE, then they essentially ask you something about the wave equation. Now PDE are of course partial differential equations. I'm Dr. Ganguly. And today we are going to look at two problems. First, we are going to solve the wave equation in the general mathematical sense, and then we are going to look at it in the physical problem, the mathematical physics problem of the equation for a string in vibration. So these are the two problems we are going to solve today. So let us start with the wave equation, which you see in red here. Now you can see here that you have to solve for u as a function of x and t. And what happens is that on the left hand side, you have the second derivative with respect to t, and on the right hand side, you have the second derivative with respect to x, and you have the term c square here. Now, of course, if you are not familiar with partial derivatives, you should go back to some of my previous question banks where I have introduced that subject. Now, one of the ways to solve such equations is the method known as separation of variables. And in this method, what happens is that we presume the solution u function of x and t can be written as a function of x and a function of t. So here I have split this uxt into x, a function of x, and t, a function of t. Now, once we do that, we can substitute this in the partial differential equation and then see how this equation simplifies to some form which we can solve. So let's do that. We substitute the expansion of uxt in terms of x and t into this equation here. And so what you can see here is on the left hand side, you actually have differentiation only with respect to t. So we can pull out the x term and we can leave only the t term inside the derivative signs. Similarly, on the right hand side, we can pull out the t term and we can leave only the x term inside the derivative, because here the derivative is only with respect to x. So remember, whenever we are taking partial derivatives, if we take the derivative with respect to t, then we have to treat x function as a constant. And in the second case, if we are taking the derivative with respect to x, then the t function is treated as a constant. So that's what has allowed us to do this particular step. Now, once I have done this step, I can immediately realize that I do not need to carry this partial derivative nomenclature anymore. I can replace it by the regular derivative, which is d here. And once I do this, my mind will become clearer, because now I can deal with regular differential equations or ordinary differential equations. So now from this particular term, I can rewrite the equation such that I bring all the terms involving time to the left hand side. I bring all the terms involving space or x to the right hand side. And I have used the dash nomenclature, for example, x double dash, to represent the second derivative with respect to x, and the dot nomenclature, that is t double dot, to show the second derivative of t with respect to time. So if I do that, I can write this equation in a compact form here. And what you will realize is that if I have a function of t and I have a function of x, the only situation where these two functions are going to be equal is if they are both equal to a constant. So this is what I am putting here. I am putting this sigma as a constant, and I am saying that the function of time is equal to the function of space only if these two are both constants. So now what this step lets me do is that it lets me write two ordinary differential equations. One is going to be in terms of time and the second is going to be in terms of x. And once I solve these two differential equations, I can go back to this term here, this equation here, and I can substitute x and t, and I can get u as a function of x and t. So that's the next step. Let's try to solve this equation in the next slide. So I rewrote that equation here, and now I can immediately write two differential equations which you see here in purple. So one of them is with respect to time and the second is with respect to space, that is x. And immediately looking at these two equations, we know that we can get exponential solutions for these problems because remember sigma c square is a constant, sigma here also is a constant. So these are essentially constant coefficient ordinary differential equations. So I can presume that x of x is a function of e to the power Rx and t of t is e to the power st. And once I make this substitution in the differential equations, I will get these equations here. So the equation in space will give me r square minus sigma e to the power Rx is 0. The equation in time gives me s square minus sigma c square e to the power st equal to 0. So all I substituted is I substituted this x of x in the second equation and t of t in the first equation, and I simplified those out. Now of course the exponential term is not going to be equal to 0, so r square minus sigma should be 0 and s square minus sigma c square should be 0. That immediately gives me r is plus minus root sigma and s is plus minus c root sigma. So these are the two solutions of these two characteristic equations. Now from these two solutions I can of course write the general solution of x and t. So let's do this now. We have r and s and I can immediately write x as a function of x as this function here, that is d1 e to the power of x root sigma plus d2 e to the power of minus x root sigma, and similarly I can get an expression for t of t as d cube e to the power of t c root sigma plus d4 e to the power minus t c root sigma. And then I immediately invoke the equation uxt is xx tt, and I get this equation here which I have given in green, which is the general solution of this partial differential equation provided sigma is not equal to 0. Now that is a special case which I am going to look at in the next slide. So what happens if sigma is 0 is that these two equations here will simply become 0. So in that case I can write two equations. One of them will be x double dash x equal to 0 and the second is t double dot t equal to 0. So from this I get the solution x of x is d1 plus d2x and t of t is d3 plus d4x. So remember all I did here is that I integrated this expression twice, and so I ended up with this here. Now once I get these two expressions I can immediately write the solution here, and the solution is going to be in this form. I'm going to have this function of x here d1 plus d2x multiplied by d3 plus d4t. Now let us write down both these equations or both the solutions. For the sigma 0 case, we have uxt given by this expression, and for sigma naught 0 case, we have uxt given by this expression. Now the interesting thing here is that there are four arbitrary constants d1, d2, d3, d4 which need to be estimated, and it's through these constants that the physics of the problem comes into the mathematics. That's how the physics talks to the math. And two of these are going to come from boundary conditions, that is those which depend on x, and two of these are going to come from the initial conditions, that is those which depend on time. So that's what's required to be found for many practical problems. Now let's take this equation to an actual practical setting, because most of the time we use partial differential equations are because they come out of some physical problems, especially problems in mathematical physics and engineering domain. So one of the simplest PDs of course is the wave equation, and that directly applies to string vibration. And so now the question is, solve the wave equation for string vibration with boundary conditions u0t is 0 and ult is 0. So here the equation remains the same, and what happens here is that there is a string which is of length L, and so at the two ends of the string, that is at x is 0 and x is L, the string is essentially constrained. It's fixed at these 2 points, and therefore the displacement here is 0. So u here represents displacement. Of course, x is the coordinate along the length direction of the string, and t is time. Now, what we do here is that we again simplify it in this form which we did previously. But what I'm going to assume is that I'm going to say that sigma is minus omega by c square. And why I presume this is that I know that this is a vibration problem, so I'm going to get the solutions in terms of sines and cosines, and that's going to simplify my life. Of course, you could also do it in terms of sigma. You could use complex exponentials and get this result, but this is the form which is given in most texts and in places where we are looking at vibration problems. So if I take this particular value and substitute it, I'm going to get two differential equations again. I'm going to get an equation in time and I'm going to get an equation in space. I can immediately solve these equations to get x and t as functions of small x and small t, or space and time respectively. And so I get the general solution in this form. Again, I have four constants here: d1, d2, d3, d4. So now let us bring in the physics of the problem and apply the boundary conditions. So like I mentioned, there is a string like this here. The string starts from x is 0 and ends at x is L, and the displacements at these 2 points are 0. You also remember that for the string, what happens is that c is actually a physical representation. So c can be written as root of t by rho, where t is the tension in the string and rho is the mass per unit length. Now we substitute these two boundary conditions in the equation here, the solution in green. And so the first equation gives me this value here, because what's going to happen is that when I substitute x is 0, then one of these terms is going to become 0 and the second term is going to become 1. So remember, cos of 0 is 1, sine of 0 is 0. So I'm going to only have d2 in this equation, and this whole thing should be 0. Now, of course, if this thing is to be 0 in the general case, then d2 should be 0. So this in pink is the first condition I get out of the boundary condition. Now the second case is ULT equals 0. So I substitute that. I know d2 is 0, so that term is not required. So I get this equation here. Now for this equation to be 0 and to have a non-trivial solution, I would not like d1 to be 0, and certainly I don't want d3 and d4 to be 0. So what will be happening is that sine of this particular value, that is omega L by C, this should be 0. So this is the equation which comes out of the second boundary condition, ULT equal to 0. Now this second equation is going to tell us more about this problem. Now before we move to that, we'll just summarize the fact that the solution at this point has become d1 sine of this particular function of x and the function of time, because d2 has been set to 0 from the boundary condition. Now of course we have sine of this particular value to be 0. Now remember that omega here is the frequency, sometimes known as the radial frequency, and this is equal to 2 pi f, where f is actually the natural frequency of this system. Now in that case also one more relation is there, that is the wavelength lambda is c by f, and c is of course root t by rho. So from these equations we can get some more equations. One of them of course is going to be that whatever is inside this sine function, this should be equal to n pi, because those are the points at which the sine function is going to be 0. And then we immediately can write some more equations. We can substitute this radial frequency by 2 pi f to get 2 pi f L, and c becomes lambda f from this equation. So I get 2 pi L by lambda, and that is also equal to n pi. Now remember, there are an infinite number of these frequencies out there. So this is a continuous system. So there are going to be an infinite number of natural frequencies of the system. So from this equation, I can then get that Fn, or the natural frequency in hertz, is omega n by 2 pi, which is n by 2cl into c. And then I can immediately write this as n by 2cl n by 2L into root T by rho. So this is the natural frequency. If you calculate it using the proper units, then you are going to get the answer in hertz. And of course, as far as the radial frequency is concerned, that is going to be in radian per second. Now, this is the natural frequency of the system. Of course, there are n natural frequencies given n is 1, 2, 3, and so on. And also this function x of x, which is sine n pi x by L, this is the mode shape for this wave equation or the equation for the string, because we see here from the displacement that you are going to have this shape sine omega x by c, and therefore if I substitute this natural frequency with the frequency here n pi by L, I get this particular equation here. So these are the harmonics. So depending on n is 1, 2, 3, 4, and so on, you can plot these mode shapes. These are again very important aspects of any vibratory system. So we saw how the partial differential equation gives you the natural frequencies and mode shapes of the system when you apply the boundary condition. And of course, if you want to find the coefficients D3 and D4, you have to find what are known as the initial conditions for the problem and then substitute that. So that would be the situation where maybe the string has been moved to some point and then it has been released from there. And so that may give you the initial conditions.